pavement engineering and materials to share their insights and expertise as a speaker in this webinar series. And in fact, the core objective of this initiative is to expose our students and researchers and faculty alike to the forefront of research and the latest advancement in pavement materials and structure through this webinar series. And today is the ninth episode of this webinar series, and the title of today presentation is the performance of stone-based materials at large deformation. And our today speaker is Dr. Denis Jelagin from KTH Royal Institute of Technology, Sweden. Dr. Jelagin is currently an associate professor of highway and railway engineering at KTH Royal Institute of Technology. He is also responsible for the transportation infrastructure thematic area of KTH Trino multidisciplinary research environment at KTH for holistic transport, research, demonstration, and innovation. Denis obtained his PhD degree in solid mechanics from KTH in 2008, and since then, his research activities are focused on mechanics of infrastructure materials, as well as on structural mechanics and structural design of roads. Presently, he is engaged in several research projects aimed at improving performance predictions and optimizing structural and material design in infrastructure application. He has over 60 publications in peer-reviewed international journals on various aspects of infrastructure engineering. And currently his technical focus is on mechanics and material design of stone-based construction materials for roads and railways, discrete element modeling of stone-based materials, structural design of roads, and vehicle road interaction. So thank you so much, Denis, for accepting my invitation. It's indeed a privilege to have you in this webinar series. And before starting the presentation to our audience, I would like to mention that this webinar will be a start with the presentation by Denis, and then it will be followed by a Q&A session. So whether during the presentation, you might type your question in the chat box, and then after presentation, I will read the question, and hopefully Denis will answer your question, or you can directly raise your hand, turn on your mic, and directly ask your question from Denis. With that, I give the floor to Denis. Thank you, Denis. Yeah.
So, thank you, Ali, for introduction, and thank you for organizing this seminar. It's a pleasure being able to share our research at KTH with researchers from Jelagin University. Do you hear me well?
Yes, yes, we can hear you. Yes, thank you.
Yeah, great. Let me share my screen. Yes. So hopefully everything works now.
Yes, we can. Yes, I can see. We can see your screen. Thank you.
Great. So good day, everybody. And today I'll present our research on development of new experimental and modeling tools to gain better insight into mechanical behavior of stone-based materials at large deformations. And by stone-based materials, what we understand is materials where crushed rock aggregates provide main load-bearing capacity, at least in compression and shear. So that includes dominantly asphalt and unbound road and railway materials. We also have some projects on railway side. but also in principle, it should be easily extendable to materials like concrete, etc. But so presentation is a little bit, probably a little bit unusual for a pavement engineering presentation. I will not speak too much about one particular civil engineering aspect. I will rather focus on instruments, what we can use to develop better solutions in future. But before we start with the technical contents, a little bit of info.
Sorry, Denis, for interrupting you. I'm not sure whether you are moving your slides because we cannot.
How about now? Now you should see a slide called Sweden info. No?
We are still on the slide one. This what the screen shows in on slide one is not moving.
Strange. Let's
I think I think you are using the web version of Teams. Am I right?
I do, because I cannot install app on my laptop. I don't have.
So that is the reason. Yeah, the web version. Then this is the issue with the web version. But unless you do it, I mean, manually, just a slide by a slide, do it. It will be moved. Otherwise, it will not automatically will move.
So you still see the first slide only, right?
Yes, it is first slide. Yes, what I can see is now first slide.
Should we?
Yes, now it is the now is a little move. Yeah, and
now now you probably see the whole app, right?
Yeah, this is no, it is not full screen, and it is still just first slide on first slide.
But now
yeah,
I
now
can
yes,
see.
this is the second slide now.
Yeah, let's see. Let me try once again. So if I start from here, do you see? Right. Yeah. Do you see Sweden info right now?
Yeah, I can see the second slide, but it is not full screen. But I can see.
Is anything moving right now?
No. It is the web version. This is the issue with web version. Yeah, so that is why we have previous experiments. Yes, experience that yeah, web version is not working like.
That's unfortunate.
Yes.
If I keep it in, if I do it like this, if I switch to presentation mode, but then if I stop sharing, let me. We'll try one final thing, and then if it doesn't work, I'll have to survive without presentation mode somehow.
Okay.
No, it will be the same thing probably. How about this? How about now?
Yes, yes. Now is working. Showing the animation is now showing. Okay, yes.
Good.
Okay,
good.
Great. Thank you. Great.
Just in future, if somebody else will have the same problem, if you switch to share entire screen instead of sharing one window, apparently it works better.
Okay. Thank you.
Okay, so some general information about Sweden. Sweden is a reasonably large country in European scales. We are actually fifth large country in Europe, and you have it here highlighted on the map in red. We are not Switzerland. We are being mixed up quite often. So small country in the center of Europe with expensive watches, that's Switzerland. Big country up north, cold one, that's Sweden, that's us. Population is 10 million, so for such a large territory, we don't really have a lot of people. But in spite of being a reasonably small nation, Sweden is quite research intensive. Probably at least some of you know Sweden is home of Nobel Prize delivered at the end of November each year. And Sweden is also home to few innovative companies. Probably most of those brands are recognizable even internationally. Earlier on, Sweden was very active in vehicle technology, so Scania, Volvo are big brands. Then, of course, we've got IKEA, Ericsson on ICT side of things, and lately Sweden also moved into IT and computer science quite a bit. Maybe to the younger part of the audience, Minecraft is a familiar brand. I'm not sure those things that go in and out of fashion quite fast, but at least my son, when he was small, he played quite a bit of Minecraft. If we are to look into a road section more precisely, we have quite a developed road network, and you see some numbers on the screen. Those numbers should be compared with 10 million total population. So we don't have too much of taxpayer dollar per kilometer of road, which puts additional pressure on us in terms of being able to build and maintain our road network in economically efficient way. We have a few challenges which are a little bit unique. Probably the first one is a relatively high total vehicle weight allowed on Swedish road network. In Sweden, mining and timber industry are quite big parts of industrial landscape. And those industries, they do benefit a lot from being able to transport heavy loads with a single vehicle. Those things are also good for labor productivity, for increasing standard of life. The only way to increase standard of life in long term is being able to work more productively, and heavier duty vehicles, high capacity transport means that one driver can transport more load, means being more productive. So 60 metric tons until 2019, and from 2019, total vehicle weight is limited with 74 metric tons. And this is done by increasing number of axles. So we use those very long axle combinations with 8 and 9 axle vehicles. So the axle weight limit doesn't change, we stay within 10 tons so far. It is also not unusual to have special cases where we have roads kind of dedicated to timber production or dedicated to transporting iron ore, where they get special permits for even heavier vehicles. And then, of course, the other big issue is everything related to cold climate. So here on the picture, you see temperature regimes we use for pavement analysis in Sweden. And as you can see, especially zone number 5, climate zone number 5, which is up north in Sweden, we deal with negative temperatures throughout quite big part of the year. One big issue is studded tire traffic. So this is what you see here on this picture. So those tires, I know that it's not familiar to everybody in China. To provide better friction, better grip during winter road conditions, one instruments tires with steel studs. And while those studs can be quite beneficial for safety, they are not necessarily very good for the road wear. So dealing with road wear from studded tires is a big topic for Swedish conditions as well. Now a little bit about university I represent, KTH, or Royal Institute of Technology. So KTH stands for the Royal Institute of Technology in Swedish. This is oldest and largest technical university in Sweden, and here on the picture you see part of the main campus building. We used to say that we are our largest technical university in Nordic countries, but by now it changes every second year. Every second year, NTNU in Norway is somewhat bigger, and sometimes we are still the biggest. You see some numbers on the slide with respect to number of students, PhD students, and staff. We are quite research-intensive university, so we have a lot of staff per student. And we are concentrated to Stockholm area. We have 4 campuses in Stockholm, in different parts of Stockholm, Swedish capital. And here at the bottom, you see a picture of Stockholm during summer. During summer, it is a very beautiful city. And every year, we get at least one student on Chinese scholarship council. So if you'd like to consider it, I know some of those attending the seminar are students. You are definitely welcome to apply. One thing which is a little bit special for our university is that our research, in addition to standard structure where we're organized into schools, departments, research groups, etc., we are also organized into 5 multidisciplinary focus research areas, and those are life science, materials, energy, internet and communication technology, and transport. So this is an outcome of research assessment exercise, which was performed 12, 14 years ago, where external review panel tried to find match between available research capacity at KTH and societal challenges we face in the future. And of course, I am being a road and railway engineering professor. I work with research area of transport. And that's a multidisciplinary focus research area with a lot of researchers at KTH. In total, we are more than 800 people with 40 different research teams. But of course, not all those people are on infrastructure side. Actually, most of the researchers we have are on vehicle technology side of things. Sweden being traditionally very heavy on vehicle development. Vehicle technology is a big area of research in KTH. We also have people working with transportation systems, logistics, transport economy, etc., policy. And we also have infrastructure engineering, including roads, railways, tunnels, bridges, etc., etc. So within this infrastructure engineering, we also have my research group, and we are 6.5 people. Presently, we have 4 PhD students, 1 postdoc. We have 1 guest professor, Manfred Bartel. He is quite active, and me as associate professor. We have infrastructure laboratory connected to the group. In terms of the budget, we're around 8 million Swedish crowns, which is around 6 million yuan, I want to say. And budget comes roughly 50-50. Half comes from research project we perform mainly for Swedish Transport Administration, but the other half comes from funding available through national research councils, Vinnova, which is Swedish Innovation Agency, and base funding from KTH. In terms of research we do, I myself, I'm not a civil engineer by background. I've done my PhD in solid mechanics, actually working with fracture in glass. Spent some time quantifying what happens when stone hits windshield of a car. And this is what I do in my research nowadays in road engineering as well. I try to see how understanding mechanics of our materials and our structures can help us to end up with more sustainable, more durable structures and materials. So mechanics-based pavement analysis, material mechanics, material design of infrastructure materials. We also work quite a bit with vehicle-road interaction. And the reason for that is that, after all, we build our pavements to be driven at. Their function is defined with respect, the function of the road structure is defined with respect of being able to provide safe, energy efficient, and comfortable transportation. We do some work on non-destructive testing, and of course, sustainability in pavement engineering is a big question for us as well. We have quite developed laboratory, and here you see some pictures on the slide. Probably the biggest piece of equipment we have right here, our X-ray computed tomography system. This one is quite unique. It has built-in loading capacities and temperature control capacities. We have small supercomputer available at the group, but we're also part of several computational and experimental networks at KTH. In terms of what we do in the lab, we have kind of two main directions. One is measuring these mechanical properties of asphalt and unbound materials in different configurations, different loading modes, etc., etc. So here probably most of the equipment is familiar to you. We have superpainting direct tensile test, TSRST for low temperature properties characterization, simple performance tester. This one right here is actually in-house developed experimental method. Anders Gudmundsson, our former PhD student, developed seismic test for asphalt mixture. So the idea here is that one hits asphalt specimen with predefined hammer, and from specimen vibrations and from how fast they dissipate, one can gain information about stiffness and a little bit about viscoelastic dissipation properties of the material as well. In general, development of in-house tool has been kind of area of interest for us for a very long time by now. Early on, from 2012, 2010 roughly, we spent quite a bit of time developing image analysis procedures to quantify data from computed tomography, so attributing different material phases to different voxels in computed tomography measurements. Lately, we also worked quite a bit with developing our own instrumented indentation type of tests, working with indentation testing of asphalt across different length scales. One example you have here, this is stiffness map obtained with AFM, but we also spent quite a bit of time working with indentation testing on larger scale, where we actually try to measure engineering properties relevant for civil engineering in the field. And also we developed our own contraption to test contact-induced deformations and damage in stone materials. One cannot see, but underneath this big cylinder, we have small spherical indenter, which is pressed into stone specimen, and then we measure deformation and damage accumulation in the material. So we can see formation of ring cracks in the material. This is SEM picture. Here we have group of ring cracks, and here we have chip formation in stone material, which allows us to gain better physics-based understanding of how stones deform, wear, and break due to contact loads. So that was our group in a nutshell. Now we go into a little bit more technical part of the presentation and start to speak about tools we develop for analysis of stone-based materials at large deformations. So first of all, when we say large deformations, we have kind of our own definition of what large deformation is. It's not this classical solid mechanics definition where angles become non-negligible. We rather look at the material where we had two neighboring aggregates at the initial configuration, two aggregates in contact with each other, and then after the deformation process, aggregates rearranged so much that they lost their contact, so they changed their neighbors completely. And those type of deformations, they happen quite a bit with our material. And of course, the very first thing one would think about is kind of material production and construction stage. Mixing, transportation, laydown, distribution, compaction, all those processes are large deformation processes. And if we deal with processes where individual pieces of material change their spatial arrangement within the material, those things cannot be adequately described based on standard continuum mechanics approaches, one needs something. We can also have those large deformations during service life in the field. We can have excessive permanent deformations both in asphalt, but especially in unbound material layers. This problem is also of big importance for railway ballast layers in the field. And as we all probably know, inadequate performance of material during those large deformation situations may lead to problems in the field. Inadequate material workability or inadequate technology used for a given material may result in mixture segregation. It may result in inadequate compaction, excessive or too little air voids, aggregate damage, and so on. And those things are known to be one of the primary contributors to premature failures in the material. This problem is also quite complicated. Even for standard road materials, we have a lot of parameters affecting large deformation performance of our material, be it the aggregate size distribution, binder content, temperature, load level, etc., etc., load level and load configuration and 3D as well. And those complexities are only increasing when we move to new types of materials, polymer modified binders, warm and cold mixes, workability additives, reclaimed asphalt, etc., etc. Those things just become more and more complicated, and it becomes problematic to rely on empirical evidence available for the standard materials. And this means that we need new experimental and numerical tools to describe material behavior at those situations, and preferably to describe it from a fundamental mechanical point of view. Hence, the main two things I will talk today is kind of a bird's eye view of the research we've done over last 10 years, kind of, on development of new experimental methods to evaluate material performance at those large deformation situations, and development of new computational approaches based on discrete element study, which discrete element method, which allows us to evaluate and optimize road materials at large deformations. And then I'll show some application examples to both unbound granular materials, but also for asphalt at those kind of large deformation situations. So here we have first example, and that's from a PhD project at KTH, which finished roughly 5 years ago, where a new test method to study flow of asphalt mixtures during compaction has been proposed. And the idea there was to remedy shortcoming of not having test method which deals with mixture compaction in kind of semi-confined situation. Everything we have in the lab so far confines mixture completely. Think about gyratory compaction, where one has a top plate which covers specimen 100%. Now, this is not exactly what happens in the field. Of course, we have a compactor wheel here on top, but mixture is not completely constrained from flow outside of this compaction wheel. And the idea with this test method was to kind of simulate the same process in the lab. So we have rectangular container where we have asphalt mixture inside, and we have loading strip applied on top of the material. So here you see this picture of the test setup in the lab. So container with asphalt mixture inside, load head with rectangular load head pressed into the material. And we also have sensor which measures the material uplift. So how much material moves up on the unconstrained side. We spent quite a bit of time developing test method and also looking at characteristics of asphalt mixture flow within computed tomography system we have in our lab. We have one example here. Let me see if I can start the movie. Basically, what we did, we used modeling material. Let's see, maybe I should turn off pointer first. Yes. So we used modeling material, kind of representation of asphalt mixture composed of glass beads, and some of those glass beads had steel wire integrated inside, so something which is easy to track. And that allows us to quantify both vertical but also lateral deformation in the material during the test. And finally, not every test can be performed inside computer tomography system. So at the end of PhD project, we also tried to develop tracking system to be used in the field or in the lab, but without necessarily need of using computer tomography system. So this test method was able to differentiate between the effect of different parameters on asphalt compactabilities. So we looked at the effect of REA gradation and binder phase properties. Here you have one example of this vertical force displacement relationship for asphalt concrete and SMA with same maximum aggregate size. And as you can see, SMA requires significantly more force, which is kind of expectable due to kind of gap-graded nature, as compared to asphalt concrete to achieve the same level of compaction. We also looked at different compaction modes, monotonic compaction versus kind of vibratory compaction, where compactor load is applied along with sinusoidal vibration superposed with monotonically increasing load. And one can see in the test that both this vibration both reduces uplift significantly and also affects vertical deformations in the material quite a bit, both for SMA and asphalt concrete materials. So reasonably simple test method, in our opinion, more representative to what happens in many field situations. One experimental tool which has been proposed a few years ago. Another test method we developed recently, actually Fong Chen, at that time postdoc at KTH and now associate professor in Southeast University in Nanjing, worked on it. So here you have part of Professor Chen working with the test. So the idea was to adapt slump flow test available for concrete materials to adapt it to study flow of unconfined asphalt mixtures. Here the idea is a little bit different from the previous test. Here we really aimed for something simple, yet being able to capture flow characteristics of completely unconfined asphalt mixture. So situation representative for pouring, transportation, mixture placement, etc., etc. And then this test was early on aimed to be used to validate and calibrate discrete element models for those situations. And this is how example of experimental findings look like. Here we look at SMA 16 with different binder content. So first thing we noticed early on that in contrast to concrete, we cannot look at slump ready because asphalt tends to deform differently. Some of the stones will disconnect and roll very far. So we discovered that way more representative measure of asphalt flowability is actually to look at slump height instead of slump ready. So here we looked at different binder content from 0%, so pure unbound material, 3.1, and all the way to 6.1% at two different temperatures, 155 and 135 degrees Celsius. And this is how the results look like. So on the vertical axis, we have slump height, and on the horizontal axis, we have bitumen content. And you can see that when we start adding bitumen to unbound material, of course, we provide certain amount of adhesion to the system. And for a while, this means that slump height starts to increase. Higher slump means more resistance to flow. But then at some point, when binder content is high enough, what it does, it reduces friction between aggregates significantly, and this means that slump height drops quite a bit. This is also when we start to notice the effect of temperature very obviously on our results. So here you have two lines at 135 and 155 degrees Celsius measured. So that was a little bit on experimental tools to study mechanical behavior of asphalt mixture at large deformations, but this process is very complex and we have a lot of parameters which affect the response. We have, of course, aggregate parameters in terms of size distribution and shape, and we have and by far aggregate parameters, aggregates being the main component in asphalt materials, their parameters dominate response at uncompacted state. But also bituminous mastic, the binder phase, mixture of bitumen and fine particles, affects the response quite a bit through two main mechanisms. Bituminous mastic lubricates frictional contacts and improves flowability, but at the same time it provides adhesive and cohesive bonds between particles, which means that it can also decrease flowability of asphalt mixture. And those bituminous mastics properties are in turn significantly affected by a bunch of material properties: viscosity, adhesive and cohesive strength, the amount of binder available, coating thickness, and environmental properties in terms of temperature and mechanical loading. And this is where numerical modeling based on discrete element method allows us to isolate those different parameters within simulation and study their effects independently. And it also allows us to extrapolate experimental findings we obtain in the lab to wider range of field situations with different loading scenarios more relevant for the field, a little bit wider range of materials, etc., etc. So, discrete element method. I'm not sure how many of you are familiar with discrete elements, so just in case, this is discrete element method in a nutshell. So on the left-hand side, we have a picture of our, in this case, unbound material, so collection of stone particles. And in contrast to finite element method, where we represent material as a continuum, in case of discrete element method, we represent material as collection of rigid particles of a given shape and size distribution. So here I show examples with spherical particles. Those particles do not deform, but they can penetrate into each other if compressed with a given force. And this amount of penetration will be somehow dependent on the amount of force we apply to a given contact. They can also do, if they are loaded tangentially, they can slide with respect to each other. And if contact forces become excessive, particles can break. This particle breakage can also be modeled in different ways. So basically, those contact and particle damage laws are the two main parameters which completely define the physics of the system, and they are extremely important. Basically, what we are after is developing accurate contact and damage laws of the particles. We are trying to capture this contact configuration, which exists inside real material, to well, let's say one stone with very complicated surface in contact with several other stones. But we want this particular contact, for instance, here, behave exactly as our two-sphere contact pair. So we need to define laws which provide us a relationship between normal force, P, applied to the two particles, and overlap between those two particles. We also need tangential contact law, tangential force T, and shear displacement S. And we also need the particle damage laws with respect to weird contacts and fracture of the particles. In general, there are two schools of thought with respect to contact laws. Sorry. One school of thought says that let's just assume let's just assume some kind of functional shape of the contact law and then feed parameters from macro scale experiment. Let's do triaxial test on unbound material or simple performance test on asphalt mixture or compaction flow test and adjust contact law parameters until we get agreement with macro scale observation. And that allows to do quite a bit relatively simple procedure. But with this type of approach, it becomes kind of tricky to extrapolate to load levels outside of experimental procedure used to calibrate contact and damage loads. So we decided to go in a different way. We decided to actually look experimentally and numerically at what happens at those stone-to-stone contacts. We performed experimental study with indentation tests. So experiment is kind of shown here. We take flat stone plate and indent very stiff ball made of tungsten carbide into the material. And we've done two different types of experiments. We've done cyclic contact experiment where we apply load over 10 cycles to the material, relatively small load. And this is how, and we measure applied load and stone deformation. So this is what you see here. So during load application, material is being loaded. Once we unload, there is a blue line underneath the red ones. So we end up with quite a bit of dissipation during first loading cycle due to asperity corrosion. This dissipation kind of goes away, so the red lines are the lines measured at the second cycle. So in the second cycle, we have way less dissipation and pretty much no permanent deformation accumulation of the material. Overall, this thing kind of follows well-known Hertzian relationship, except for this type of small dissipation amount available, and we also have a little bit of linearity in the beginning due to asperity corrosion. So contacts tend to become stiffer. They stiffen during the first cycle, and then they keep increasing in stiffness a little bit with load cycles, and dissipation drops as shown here. We also done monotonically increasing loading tests where we apply load and keep increasing the load until material responds with fracture. What we see experimentally, we see jumps in force displacement curves like that, and those jumps are also accompanied by acoustic emission. After those jumps, we cannot see too much at the stone surface. We see a certain amount of ring cracks, so-called Hertzian cracks on stone surface, but those ring cracks cannot be responsible for the jumps. So hypothesis was that it's mostly due to median cracks propagating under the indenter downwards in the specimen. And those cracks can actually fracture the stone completely. So this type of experiment that actually allows us to measure those that fracture resistance in contact situations. But this is done at one particular geometry, so we need to generalize somehow. And for that, again, we need modeling. In this case, finite elements, because we deal with stone as continuum material. We zoom in now into one contact points. And this is kind of, again, it's kind of bird's eye presentation, but I always have references on the slide, so feel free to take a look at the pictures, at the papers, and for more details. So we proposed a model based on so-called KST-DFH model, elastoplastic model with anisotropic damage, to describe indentation process in stone. And what one can see here, the black line here is experimental line, the one we measured in the lab. Red, green, and blue one are from the experiments obtained with different friction coefficients. And as you can see, the model captures dissipation quite well. The model also captures fracture forces. So blue and red lines here are simulated force displacement response. As you can see, we can capture those jumps in force displacement curves quite well. And those jumps correspond to formation of those median cracks in the material. So here we have stone to indenter contact area. This red stuff on top are Hertzian cracks, so ring cracks on the surface, and then they propagate into cone. And those big cracks, they form unstably, and those are the cracks corresponding to those jumps in force displacement curves. The crosses are experimental laws from experimental study. So basically combining those indentation experiments and the finite element modeling allows us to come up with particle damage laws, which are generalized for arbitrary particle geometries. So in spite that in many of our simulations we use spherical particles, they deform and fracture in a way irregular particles will deform and fracture. So this is how contact law we proposed for discrete element simulation looks like. Here on top you have experimental results, and at the bottom you have our contact law proposed here. We capture both dissipation during first cycle, so pretty much the only experimental finding we ignore is dissipation during the second cycle. I think somebody is not muted. Still not muted. So we have our fracture criterion based on where each particle is assigned individual normal force, which is based on those most experimental values. We really need to mute somebody. Let me see. Okay, maybe not. No. Mm.
It seems someone should be muted. Yes.
Yeah, I'm trying to. In the list, it looks like everybody is muted except me. But
yes, yes, it is exactly what I see. But also same, but I don't know.
Okay.
Okay, so
we continue. So we assign those critical forces based on combination of experimental study and those numerical results. So here you have results from experimental study, measured fracture forces for different materials, and we have our image-based modeling simulations. Now, that was for the contact law between two aggregate particles. In case of asphalt, the story becomes more complicated because in addition to aggregates, we also have viscoelastic phase. And for that, we propose kind of two-term law based on elastic aggregate particles coated with viscoelastic binder phase, published in Powder Technology in 2018. And the idea there is that if we look at stones, at some point we have this nearly Hertzian contact shown here with blue line. But in case we have a certain thickness of the binder film, we have viscoelastic deformation until a certain depth. We have much softer response, and this part is rate dependent, so it is viscoelastic until we reach binder film thickness where elastic deformations take hold. Now, just to show some results from numerical simulations, and we've done few simulations in different studies looking at compaction flow test, gyratory compaction, and slump test for different materials with different gradations. So the first example is from modeling compaction flow test, and here we have black lines. They come from experiment for SMA with two different binder contents, 4 and 6%. And the red and blue line comes from numerical simulations with discrete element method. This is very good agreement, given that we have not recalibrated anything on a macro level. So basically, all the input parameters come from characterization on component level. We also capture uplift quite well. So the lines on the graph show uplift as obtained in the modeling. And there we have access to the full history of uplift. And here we have 2 points coming from experiments. In experiments, we measured uplift only at the end of the test. And again, agreement is at least qualitatively in a ballpark of what we predict. This is actually as good as it gets with such a unrepeatable material as uncompacted asphalt mixture. We also looked at gyratory compaction, where we both looked at air void evolution during compaction process. Again, black line comes from experiments, and colorful lines are asphalt concrete and SMA obtained at different binder contents, etc. And the discrete element model also allows us to gain insight into aggregate breakage during compaction process. Not too much aggregate breakage happens during those gyratory compaction simulations, as those loading scenarios are designed not to break aggregates excessively, so that's kind of expectable. We've also done simulations of compaction flow tests. So here we have experimental procedure where one simply fills this slump cone with asphalt, and then one moves, slides cone up and sees how asphalt flows. And the corresponding process is applied within discrete element simulations. Now, in discrete elements, of course, you cannot see the binder part of the story because that one is integrated into contact and separation laws. Agreement between experiments and simulations is quite nice. So here's the green line is the experiments at 135 degrees Celsius, and dashed red line is from discrete element simulations. And you can see that at least we capture the physics of the process, so kind of increasing the resistance to flow and then dropping resistance to flow at further increase of binder content. So this means that we have reasonably high hopes, expecting that the model will also capture asphalt flow in different scenarios. What happens during spreading asphalt in the field, what happens during transportation, and so on. There is a follow-up study to this one where we looked at the segregation of asphalt mixtures during transportation, etc., etc. Finally, I have one final example, and that's looking at a little bit different type of large deformation situation, and this is where we look at aggregate breakage in unbound road layers. And there it's a well-known problem that aggregate breakage may affect pavement surface life significantly. It may induce excessive permanent deformations in unbound road levels, compromise their load-bearing capacity, and reflect in pavement distresses. And the way we deal with this problem practically right now is through empirical performance tests, such as Los Angeles abrasion test. But there are a lot of different variants of those ball mill test type of thing. And those tests, they do allow us to kind of screen materials with guaranteed inferior performance. But at the same time, there is a big discussion about the relationship to field performance of those tests, and it's not necessarily very strong. And also, having this type of index value does not allow us to quantify the influence of different parameters, load magnitude, material parameters. Okay, you have material B, which is worse than material A. Can you still use it somehow further down in the structure? How much will it affect performance? All those quantitative questions are not addressable with empirical test methods. Hence, this is an ongoing project at KTH. We developed our kind of combination of experimental and numerical procedures where we measure aggregate crushing in the lab in uniaxial compaction test shown here. So we have steel cylinder where we load certain size distribution of aggregates So we do sieve test before the test, and then we apply controlled compressive load to the material, loading material with roughly 20, 30 kilonewtons, etc. And then we perform sieve analysis after the test, and we see how much material has broken off. So this experiment is used to validate discrete element modeling of the situation. And once we have our discrete element model of lab material performance validated, we can use it to predict what actually happens in the field in a controlled layer. This is how procedure looks like. It is, of course, incremental. We have all our input parameters and our discrete element model, gradation, porosity, aggregate stiffness, and aggregate fracture toughness coming through contact and damage laws. And then in each force increment, we extract contact forces at aggregate to aggregate contact pairs and compare them with our failure law. And at a certain point, when given aggregate reaches its strength, we end up with fracture of the materials, and the crack aggregated, it is illustrated by making them pink. And as you will see here in a second, also when aggregate is big, it affects overall macro scale response of the material, of course, because bearing capacity of broken aggregates is compromised, so material can settle further down in the structure. And as a first step, we need to identify parameters for contact and damage laws, and we use the same functional shape identified from previous studies. Now what we do, instead of running a bunch of indentation tests, we are reasonably confident in functional shape of our contact and damage load. So we have 4 parameters: Young's modulus, which is identified by fitting discrete element simulations into the initial part of the measured response. So dashed lines here are the lab measurements, and we have our discrete element simulations without any aggregate breakage. We see which Young's modulus for aggregates gives us best fit at the beginning of the loading process. Once this is done, we can go further and identify failure law parameters, variable stress, and weakening coefficient. And this is those parameters are identified by fitting the rest of force displacement response and so-called breakage index shown here. A breakage index is measure of deviation of gradation curve after the test as compared to the gradation curve before the test. Bigger the deviation, more aggregate breakage we had. So the 3 bars here are the kind of results of our parametric study, and the red one is from the expectancy. And finally, we can determine variable exponent. So everything is, of course, statistical with unbound materials. So we also have parameter controlling the width of variable distribution. And that we determine by trying to match experimental and numerical scattering. So I'm almost on time. I'll just show some final examples of computational results. So here we have simulations of particle breakage for single size unbound material. And those are the ones which were used to determine input parameters for the failure law. So here on top, you can see the force displacement response. Blue line is numerical model, and dashed lines are experimental results. And we have distribution of fractured particles in the material. Then we run our experiments and simulations for dense gradation, and this is where we have not performed any additional calibration. So now we use parameters identified for a single size material. And you can see that force displacement response is captured reasonably well, except for very high level of compaction. That's when we have quite developed breakage in the materials, then things start to deviate. And we are also able to predict the distribution of broken particles within the material. One nice thing with discrete element simulations, which is kind of unique, is that you can also gain kind of micromechanical insight into the processes in the material. You can, for instance, see which sizes break more, within the material. So here we could see that breakage process is dominated by coarse aggregate particles. And we can also compare the amount of aggregate breakage. So here we have this breakage index, the amount of deviation of gradation curve before and after the test. And the solid lines are lines from numerical simulations. That's where we can see the full progression. And as experimentally, we can only get snapshot at certain contact load levels. We have one snapshot for single gradation at 20 kilonewtons and 35. And for dense gradation, we have a snapshot at 35 and 50 kilonewtons. And you can see that for dense gradation, where no additional calibration has been performed again, the model captures experimental results quite well, which is good indication that contact and damage laws we developed capture the physics of the system reasonably accurate. So that was a little bit on different aspects of large deformation behavior of different stone-based materials. I am now we have 5 minutes past 10, so it's probably time for me to finish. Thank you for your attention, and of course, I'll be happy to answer questions.
Okay. Well, thank you. Thank you so much, Denis, for your really insightful and very thorough presentation. I learned also a lot about your presentation. Thank you. Very interesting to see this the progress in terms of the modeling and simulation of large deformation in stone-based material, which is very quite the very trendy topic, and I believe it's very important in the long-term performance of asphalt mixtures or stone-based materials such as base, sub-base, and etc. Okay, so now it is now we are now in a Q&A session. I would like to ask if among our audience anyone has any question, please directly whether raise your hand or you can also type your question in chat box. Okay.
I think we got one, yeah?
Yes, we got okay from Hamza. It appreciate first you for the presentation. He has some question. The first one: Can wood ash? Question is that can wood ash, silica foam, fly ash, and plastic aggregates be used in highways if we replace them partially with cement and natural aggregates such as sand and stone in concrete, normal concrete, or self compacting concrete or lightweight self-compacting, etc., as cement is not eco-friendly?
Yeah, they can and they are used to the best of my knowledge a little bit. Well, fly ash is used as a filler in asphalt mixtures, right? Even as of today. One thing we do now with this aggregate breakage model, one of the idea is to see if we can use construction waste in unbound road layers. So one problem which arises there is how do you quantify? Okay, those materials do not have as good resistance to breakage compared to natural rock. How do you quantify the effect of that slightly inferior resistance of the material on the performance? That's one question. And second question, as you point out, if you replace only part of the gradation, if I understand the question correctly, if you replace them partially with cement and natural aggregates, if you replace only part of the gradation, which part of the gradation should you replace to end up with optimal material performance? Well, instinct is to say replace fine part of the gradation, not coarse aggregates. But it also needs to be quantified better, both through modeling, but also experimentally. Yes, it's definitely a direction of research right now.
Okay, great. Thank you. And his second question, if we perform the flow properties on different types of concrete, such as self-compacting concrete and lightweight self-compacting concrete, and it follows the EFN ARC guidelines, I'm not sure, and also according to the codes, and we also perform the mechanical test, then it can be used everywhere in highway construction.
Okay, one disclaimer. Concrete is not my main cup of tea.
Mhm.
But if I understand the question correctly, is if you come up with an exotic material, such as mixing plastic aggregates or something else with concrete, and then you do all the standard tests and argue that if you meet the requirements, you can still use it in construction. If this is a question, then the general answer is maybe, but with care, because don't forget that those empirical tests are only part of the story. They are called empirical for a reason. They are called empirical because they have been used to differentiate between 5 to 10 available materials before. And those materials, they have tens of years of experience in applying them in the field. You don't have the same experience with respect to durability of new materials. It may flow very well, but it will not be durable in the field. So it's not that easy. It's not enough to just meet empirical requirements from in standards.
Okay. Okay, thank you. Thank you, Hamza, for your question. Thank you, Denis, for your answer.
Thank
Okay,
you.
any other question? Yes. Any other question? Okay, I have also, okay, so we got,
No, thank you.
okay, yeah, okay, thank you, Hamza. Okay, Dennis, I also have one question. I'm wondering whether you also study the effect of cyclic loading and also aging condition on long-term or the large deformation of stone-based material. Because I believe that these factors also, of course, among other factors, are can influence
Mhm.
the or a matter of concern for us in terms of the durability of asphalt mixture or pavement structures.
Mhm. Good question. Aging, we have not looked yet at. It is on the list with respect to recycling, how to rejuvenate and recycle the materials. Those things affects workability a lot. We haven't done it yet. We will at least try to start a new project on the topic. Cyclic loading, we looked quite a bit, but mostly with respect to different types of compaction type of loading, not so much asphalt in the field. After all, deformations there can be large, but they are smaller. So maybe that's where one needs to go after a combination of finite element and discrete element method. We recently finished work on a railway ballast side, and their goal was to provide industry with settlement prediction model over millions of cycles. So there one ends up kind of combining discrete elements and finite element methods because everything has its drawbacks. Discrete elements is computationally expensive too. So then when one goes to million cycles, then one is better off with finite element model.
Great, thank you. Thank you for your answer. Very interesting. And I just also want another question come to my mind. In terms of if we assume two successive layers of stone-based material, such as it can be base or asphalt mixture, then how would we expect to by this simulation and this large deformation can be really influence the condition of between two successive layers?
Well, one thing we did, it depends what kind of condition you are after. It's doable in simulations, of course. So you simply model both materials as collection of individual particles, but then you prescribe different contact laws. So in one case, you have the nice elastic contact law, and for the other one, you have this viscoelastic contact law with adhesive strengths. So it cannot separate, it can transfer from the other. This is very doable. Then what one can look at, we have a paper from last year, which we published with EAT conference. We looked at interlayer shear, how two layers of asphalt shear with respect to each other. So this is definitely doable, and they again, those contact conditions are dominating, and they can also get quite large deformations. For other effects, well, it depends a little bit what one is after. For instance, one can look at accumulation of permanent deformation in unbound layer, but having asphalt on top. That's very doable. Not something we have done yet, but in my opinion, it's not a dramatically difficult project.
Great. Thank you so much, Denis. Actually, it's interesting to also, I mentioned that I am also working on interlayer bonding and interface bonding between successive layers. So I think, as you mentioned, I think actually I read your paper. It was in RMPD journal. I think it was published, if I remember. Yeah, very quite interesting study. And yeah, it was a very new insight, and I hope hopefully in future we can find some avenue or chance to do some collaboration also in this regard.
We would be very interested. And,
yes, sure.
It would be good to continue that study. It was done kind of as a hobby study for us. We just wanted to try it. The modeling framework on at new configuration. But it would be not interlayer shear is extremely important. Extremely important.
Right.
Especially in Europe, where we don't build new stuff most of the time. We maintain. So how to maintain the network, how to prepare surfaces is extremely important. And it would be good to have a project on top of it. So we'll be happy to collaborate.
Yeah. Thank you so much. Great, thank you. Okay, any other question among our audience? There is no question. We can wrap up our today presentation. Okay, it seems there is no more question. Yeah. Okay, thank you so much again, Denis, for accepting my invitation. It was really a privilege to have you today. Really, thank you so much for your presentation. It's very informative, and hopefully we are looking forward to. I'm looking forward myself and my colleagues to seeing you hopefully in future, maybe in Chengdu, and we can have more discussion and we can continue this academic exchange. And yeah. And
thank you for organizing the seminar.
My pleasure.
I hope to have a chance to visit Chengdu.
Yeah, sure. Thank you, everyone. Thanks to our audience for attending this webinar. Please stay tuned for our upcoming webinars, which it will be notified in the due time. And so by that, please have a nice day, everyone, and see you again. Thank you, Denis. Bye. Have a nice day, everyone. Bye.